Welcome back. Let's look at the formal definition of a limit. Let f of x be defined on an open interval about c, except possibly at c itself. All right, so what does that part mean? Open interval means that the function doesn't have to be defined at the endpoints. This is in your notes, but I have put all of that writing in there for you. All right, so our endpoints don't have to be defined. We could have, instead of a filled-in circle, if you will, an open circle. They don't have to be defined there at the endpoint. So that's what open interval means. And then except where it says except possibly at c, it means f of c doesn't have to exist. Right? So we saw in previous examples that the function does not have to exist for a given value of x for the limit not to exist. Right? So we say that the limit of f of x as x approaches c is equal to L. Right, so L is our limit, and that's only true if the absolute value, these are absolute value bars, not I's or L's. They just didn't come out as tall as they should have been. So if f of x, the absolute value of f of x minus L becomes arbitrarily small when x is any number sufficiently close to but not equal to c, because we're not interested in what happens at c. We're interested in what happens as we get closer and closer to c. All right, so what does this part here mean? All right, well, it means this. Right? And then we're going to take a look at this in more detail. So I really want to make sure you understand the formal definition of a limit. We'll see it again on the next page, but just written with the formal definition without the explanations. All right, so the limit of f of x as x approaches c is equal to L if and only if the absolute value of f of x minus L, in other words, the difference between the function and the limit, gets smaller and smaller as x minus c. In other words, the difference between any x and our given x. So when we have like x approaches, so if we have, where am I going to write over here? The limit of f of x as x approaches c is L. Right? So if we take the difference between the value of our function at some point and the limit, if that gets smaller and smaller as we get closer and closer to whatever x is supposed to be approaching, whatever c is. All right, so you have this in your notes. Let's take a look at how this works and what this means with an example. Right, you're not going to be required to actually, these are called delta epsilon proofs. I am not going to be requiring you to do a delta epsilon proof. It's actually not part of Calc 1, but it helps make the formal definition of a limit easier to understand. And we're going to work with a nice easy function, so it's really not going to be difficult at all. All right, so let's look at a visual so you get kind of the idea. All right, so here we have some range of x values, right? So here we're some distance away from x, right? In this case, a is, we're looking at the limit of f of x as x approaches a. And that limit is equal to L, right? So we should get closer and closer to the limit, right? So these are all just values right here of our function. Right? If we move a little bit to the left or a little bit to the right, we're going to be somewhere in this range. If we move closer, so if we move a little closer from the left and a little closer from the right, so we get even closer to A, we should be even closer. Maybe it's going to be in here. We're going to be even closer to our limit. Right, so we can be as close to the limit as we want, if it exists, if we use x values that are closer and closer to the value x is approaching, in this case a. Right? So let's take a look at that with a proof. And our proof is going to involve this. Right? So epsilon here, this is epsilon. That's just the difference between f of whatever we're approaching. So in this case, it's a, right? So it's going to be f of a in this case. Actually, let's leave it as f of x. We'll just do it in the generic case. So epsilon is the difference between f of x and the limit. This is what we're going to be given that. We're going to be told, I want you to be within this close of the actual limit. How close do you have to be to the x value to get that close to the limit? This part here, this is delta. I don't always draw that very well. Oh, mine goes the other way. That's right. So delta here is the difference between x, any x, and our given x. Right? In this case, our given x in our diagram here is a. Right? So our given x is a. Right? So we can figure out how close we have to be to x if you tell me how close I have to be to the limit. That's all that is. The absolute value bars is because we're looking at distance. Right? And distance is positive. Right? So we have absolute value bars because this is distance. Right? And so we don't care if we're going to the left or to the right. We just want to stay within a certain distance away. All right, so let's take a look at what this means. So here you have this part in your notes. Let f be a function defined at least on an open interval. Right, so open interval means we're going a little to the left and a little to the right, except possibly at that x value itself. We might have a hole in our graph. So the limit of f of x as x approaches c is equal to L so this epsilon greater than 0, that just means if you tell me how close I have to be to the limit, I can tell you how close you have to be to x. That's really all that means. Let's write that in so that let's take it out of the formal mathematical terms. You need to know the formal mathematical terms, but let's give it some understanding for you. Right? So in other words, all of what this whole limit means is how close do I have to be to a given x. So that's all this really means up here. If the distance between f of x and the limit has to be less than this value. You're always given that epsilon value. You're told, okay, you're going to be this close to the limit. What x values can I use? How close do I have to be to x? Right? So we're going to, and here's our question, find the set of delta given that epsilon has to be less than a tenth away. So in other words, where I have this, so f of x, the distance between my function and my limit has to be less than e. E is 0.01. Right, so our first step, we have our limit. We're interested in this limit here, the limit of 2x plus 3 as x approaches 4. I'm going to move this over a bit. Boop. We're going to move that over just a little bit. And I don't have any of this written in your notes, so except for the graph. And I don't think it's graphed, but you can graph it. So you'll just kind of follow along with me. So we're going to use our graph to find our limit, right? Because this one's not too difficult. If we come from the left of 4 and we come from the right of 4, we can see that our limit is 11. So here on these problems, either the limit is given to you or the limit is that easy to find, one or the other. All right, so we know what L is, right? So in this case, we know L is 11. We know what the x value is, right? So this x, actually let's write this part out. Let me put it over here. Let me just get started actually with let me write out our limit definition, and then I'm going to fill in the blanks, because that'll make more sense than if I do it the reverse way. Right? So our limit definition, right, is right here. That's what we work with, and then we solve for our delta. Right? So we have the absolute value of f of x minus L has to be less than epsilon. Now let's fill in the values, because I think it'll make more sense if we write that first. Right? That's our first step. Right? And so this is just the formal limit definition. I'll put that underneath. And just follow along with me. Even though you're not going to be doing delta epsilon proofs, to have an example when you do have to do them will make it a lot easier. And it will make the formal definition of the limit easier to understand. All right, so now f of x, right, well, that's 2x plus 3. That's what we're taking the limit of. Right? And the L, that's 11. That's our limit. And the epsilon, well, we're given that. That's 0.1. Right? So we're going to take those values and plug them into the formal definition of the limit. Right? So we've got the absolute value of 2x plus 3 minus 11 is less than 0.1. Well, now, we have two choices. We can either simplify in the parenthesis in the absolute value bars or rewrite. Let's rewrite, because just to make sure you understand the rewrite, because the simplifying in the absolute value bars is pretty darn easy. Right? So remember, when you take the absolute value of something, right? So for instance, in our limit definition, if f of x, if that distance has to be less than e, then epsilon, it means it could be that distance to the left, or it could be that distance to the right. Right? So when we're dealing with, this one's an L, and when we're dealing with absolute value, right, we don't care direction, we just care how far we are away. Right? So I could be 0.01 to the left, or 0.1 to the left, or I could be 0.1 to the right. So when we rewrite this, right, we can be to the left, 0.1, or to the right. Right? So our distance here between our function and our limit has to be no more than 0.1 away. So now let's get rid of the absolute value bars and rewrite this. So I want to do that first because I want to talk about that, because that next step is pretty easy. 3 minus 11 is 8. Right? So we have negative 0.1 is less than 2x minus 8 is less than 0.1. Well, now we're just going to solve for x. Right? So we need to move that 8. We need to add 8 to both sides. We need to add 8, right? So now we just add 8 to everything, because we're trying to solve for x. We're trying to find those x values that'll ensure we're no more than 0.1 away from our limit. Right? So we have negative 0. Oops. Let's add 8 to both sides. So 0 minus 0.1 is going to be 7.9, is less than 8.1. So all I did was I added 8 to both sides. Now we're just going to divide everything by 2. Right? We're just dividing by 2. All right, so that's going to be 3.95. And that'll be 4.05. Right? So that's how far away we can be from x. So those are our x values. Right? So if x can be between 3.95 and 4.05, that means that delta here, right, is going to be the difference, right? Between, and it'll be the, and we don't care positive or negative, right? So 4 minus either one of those, right? Or right, either way, it wouldn't matter because the absolute value would be exactly the same. Right? So that's just 0.05. Sorry about that. I don't know what I hit to give us the keyboard. Right? So these values here, when we solve, give you the x value. You just have to subtract what x is approaching to give you delta. Right? So what that all means is that if f of x is required to be within 0.1 of the limit, which we know is 11, then the absolute value actually, I'm going to make it even shorter. Then our x has to be within, and that's 0.05 of 4, right? Because x is approaching 4. Right? So if your function has to be within 0.1/10 of the limit, then x has to be within 0.05 of that value of 4. Now if the limit is true, which it is, if I give you a smaller epsilon value, in other words, I say you have to be even closer, right? Delta should be even smaller. Our x value should be even smaller, right? We should be within even a smaller interval for x. Let's check that out. We'll do this one kind of quickly. Now that hopefully you got the hang of it. That's all there is to a delta epsilon proof. You're just finding how far away do you have to be. And if you take smaller and smaller values for epsilon, you should keep getting smaller and smaller values for delta. If your limit doesn't actually exist, you might get crazy answers for delta. All right, so here we're doing the exact same thing, right? Only this time epsilon is going to be 0.05. Right? So everything else is the same. I won't write quite as much on that. By the way, if I went too quickly and you were still writing down notes, you can simply pause me and then meet me in the next problem when you're done. Okay? All right, so let's take a look here. Now, so f of x is still 2x plus 3. And our limit is still going to be 11. We saw that from the other page. Right? This is 11. Right? And I forget to write anything down. Oh, no, epsilon is right here. All right, so again, we start off with this, the formal definition. Right? So we have the absolute value of 2x plus 3 minus 11. Has to be less than 0.05. We want to be that close to our actual limit. So how close do I have to be to 4? Right? So let's get rid of those absolute value bars. So we have negative 0.05 is less than 2x plus 3 minus 11 is less than 0.05. Right? So absolute value, oops. And we have one absolute value bar that decided to stay. There we go. Right? When we rewrite it from absolute value bars, right, we no longer, we don't have the absolute value bars, and instead we change our value that we have to be less than to being between the negative and the positive. That's just same as before, 2x minus 8. We'll add 8 to all three parts there. So this one is going to be 7.95 is less than 2x is less than 8.05. And then we divide everything by 2. So this is 3.9. And then it would be, forgetting I'm dividing by 2, 7.5. Sorry, I forgot what I was dividing by. Is less than x, right, is less than, I think it's supposed to be a 5. Now what did I say? 7.5. There we go. Is less than x, is less than 4, and that would be point, and then 2.5. All right, so now if we subtract, right, so we'll just pick either one of them. Right, so 4.025 minus 4 gives us our delta. So now delta is 0.025 is our delta. Notice 0.025, that is smaller than 0.05. Right, so if f of x, let me give myself a little bit more space. And actually, I'm going to switch colors. This is the big point here. So if f of x is required to be within 0.05, that's not a 0 in front, it's just a smudge, of our limit, which is 11, then x has to be within 0.025 of 4, right? Because that's what we were approaching. Right? So when the limit exists, if you say 0.05 wasn't enough for you, maybe you want 0.000001. Whatever value you come up with for epsilon, I should keep getting smaller and smaller values for delta. And that's the whole idea of our formal definition. So we can actually prove that the closer, and we can prove it mathematically, the closer we get to our limit, the closer delta, the smaller the delta value is going to be. Right? And the closer here, now I'm even closer, right? 3.975, 4.025, that's closer to 4 than 3.95 and 4.05 is. Right? So delta epsilon proofs, they sound so difficult, but all you're showing is that no matter how close I want to be to the limit, I'm going to keep getting closer to whatever x is approaching. Right? And if any time that didn't happen, then our limit wouldn't exist. But when we know our limit exists, this will always happen. And this is the formal definition of our limit. So I want to make sure you understood that formal definition. My examples here are not because I'm going to be giving you questions on in terms of finding delta given an epsilon, or tell me how close I have to be to x, but rather so that you understood that formal definition, which without an example can seem kind of difficult to difficult and tricky, and then when you see it with an example, hopefully it makes a lot more sense. Thanks for watching. That's all there is in this podcast. Bye for now.